I just put this slide up here on the right for folks who use Twitter. It's also on Facebook as well. This isn't me tweeting about seeing Jim Harbaugh at the basketball game. This is probably a selection of 1 or 2 articles out of 10 that I might see on a day or 2 daily basis that we just tweet. And if the title looks interesting, you can just go ahead and click on it and get the short version, and if you're interested, the long version. But this is one way to kind of stay abreast of what's going on. Green buildings, living buildings, sustainable mobility, policy questions when they affect technology and sustainability, sustainable lifestyles, etc. So those are the types of topics you might find searching for program in sustainable engineering on Twitter. We have a few undergraduates in the room. We have a 9-credit program in sustainability, which is basically a required class on sustainability engineering, and then one sort of engineering-related class in the sustainability domain, and one non-engineering class in sustainability. It adds up to 9 credits, and it's an opportunity for people to begin to engage in the topic. So I just wanted to make folks aware of that, because it's obviously the type of crew here we might be interested in this. I have always wanted to begin a talk with a funny thing happened on the way to the office, and I've never been able to do it until today. So I want to thank you for that. So a funny thing happened on the way to the office yesterday. And I'd been doing a lot of work from home. I got little kids, and my wife just started a new job, so I've been sort of primary there, doing a lot of work at home. I haven't been in the office in a while. And I walk in through the civil and environmental engineering door over there, and I see a flyer for today's event. And I see my picture there. I said, oh, that's interesting. And then I see it again. And then I see it again. And something was nagging at me, so I thought, you know what, I better read this, right? And it led, I had this talk already prepared, and I'm like, I've got to redo the whole thing now. And so that was the funny thing that happened, and hopefully that's going to be the moral of the story here. So I changed the title to reflect the flyer. Is that product process sustainable? And then the subheading, life cycle assessment versus sustainable design. So that's what we're going to cover here. So this is the infamous flyer that might have brought some of you here. What's wrong with this picture? I mean, besides the obvious, right? That may be what's wrong with it, but that's not what I'm after. And yeah, that's my name, so that's right. Noon Thursday, Johnson Rooms, Lurie. Okay, like from here down, we're cool. But there's something wrong above that in the text. And I thought that would actually make for an interesting talk. I'm not going to tell you what that is. I want you to think about that. All right, so is that new technology really sustainable? Life cycle assessment can tell you. So let's test the assertion. The two concepts here, sustainability and life cycle analysis. Now, when Leland approached me, he said, would you be willing to do a talk on life cycle analysis? Okay, I call it life cycle assessment, but whatever, of course. And I wasn't really going to talk about sustainability. But given the flyer, let's understand the relationship between the two, because I think that would be a good use of our lunch if we could demonstrate what they have in common, what they don't have in common, and then give some example. Okay, so what is sustainability about? I got a little 3-minute cartoon that I'm hoping you're going to hear.
Sustainability means that things can keep going, can sustain themselves, can continue into the future, and go on forever. From a human perspective, sustainability for our planet means that it can continue to do what it was designed to do: provide fresh air, clean water, produce food, and allow us all to have a high quality of life forever. Unsustainability means that it cannot, and that is where we are now. 20 years ago, scientists in Sweden developed a definition for sustainability with 4 basic principles. These can be seen as the care instructions for our planet. If we follow them, it is good for our planet. And because we're part of the system that is our planet, it's good for us too. The care instructions are as follows. reduce our dependence on fossil fuels and heavy metals, reduce our dependence on synthetic chemicals that persist in nature, reduce our destruction of nature, ensure we are not stopping people globally from meeting their needs. Demand for the Earth's services, clean air, water, food, increases as the population increases and living standards rise, but the Earth's ability to provide these services is declining because of the way we're living. In our search for prosperity, growth and success, we are destroying the system that we as humans are completely dependent upon, nature. We humans have become a threat to our own way of life. The Earth is a system and everything is connected: society, environment and economy. To live sustainably, we need to follow the 4 care instructions and apply them to everything we do at home and at work. If we can follow these care instructions, we can work together to be sustainable. We will all have a better quality of life. We'll waste less, we'll pollute less, and we'll create more things we value in society, while improving our planet's chances of providing us with the very things we need to survive.
Let's ask you, what's sustainability about? Definition? This is the North Campus Sustainability Hour for those of you who didn't see the flyer. Actually, didn't say it on the flyer.
No, it didn't.
If you saw the email, what is it? Good.
Doing something repeatedly, being able to continue something, basically.
Being able to continue doing something, right? Sustainable. I think that's actually a pretty good definition. We have to define the something in this case. The something would be continuing a standard of living that we would find acceptable, right? So having the resources available to us, those resources might include energy, materials, clean air, clean water, but with a key recognition that only about, you pick your percentage, 5% of the world or maybe less live at our standard of living. So there are billions, literally, of people who don't live at our standard of living, who would aspire to, and don't have the means. And if they did what we do, we don't have enough resources, period. So in that sense, we're not in a sustainable position as humanity. So if we try to break it down into an equation, because we are on North Campus and engineering's big up here, right? So this will be the only equation of the day. It's a dimensional analysis, and it talks about this environment issue. Now you could take, resource impact here or air quality. I mean, you can put whatever environmental impact you want on the left-hand side as long as it has a dimension, and break it down into 3 terms: population, gross domestic product per person, and environmental impact per unit GDP. And if you do, you've got people canceling with people and GDP canceling with GDP. So you get environmental impact equals environmental impact, and that's fine. So population increasing, right? Standard of living, we'd like it to increase, right? And for so many people in the world, billions, it needs to increase, right? So we've got some upward momentum over here. If we want to modulate the upward momentum, then we have to do something about the environmental impact per unit of standard living. Now, I'm saying standard of living instead of GDP because we could start to think about what actually makes us happy and maybe put another metric of quality of life here than just GDP. I think we all know there's more to life than money. So we have this term over here, which is the idea of reducing environmental impact for the goods and services that we produce. Right? Is this a technology issue? Let's vote. Who votes yes? Who votes no? Okay. So people who vote no, why is this not a technology issue? If I'm trying to get from home to work to produce GDP, let's assume, I guess you bought lunch, so there's some GDP here as a monitor. So yeah, actually GDP increased because of this meeting. So how I get here to deliver the lecture in a car, right? What that car is technology, right? So that's part of it, right? You can think about the food system, the projector here, right? The composting plates, and these are technologies in some sense, right? So people who said it's not a technology issue, what were you thinking? Good.
Societal.
It's not just a technology issue.
Right.
Right?
And it's societal too, because why are you coming here to work, right? In, say, 200 years ago, you would work very close to where you live, maybe even where you live.
And GDP wasn't as high, right? So we could talk about it. So technology is strongly correlated with that, but it is a people issue, right? I mean, it's one thing to have windmills and electric cars and living buildings. It's another thing to deploy them, right? And that's a societal issue. And the playing field by which some technologies make it into practice and other ones don't has a lot to do with policy, right? Another societal issue, right? How do we govern ourselves? How do we balance the needs of today against the needs of the future? Because that's what sustainability is all about, right? So it is a technology issue, but it's not just a technology issue. So we talk about the triple bottom line, right? The bottom line is money, right? But we say in the sustainability businesses there's more than that, right? What's called the triple bottom line. There's the planet and the resources we need to bring everybody up to an acceptable standard of living. There's the number of people that need to be served. Then there's how well they're served, prosperity, right? 3 Ps, people, prosperity, planet, triple bottom line. But the relationship that governs how people and prosperity affect the planet is really through technology, business, policy, in a broad sense, society. Right? We call that the triple bottom line. So coming back to the flyer now, right? So is that technology really sustainable? Right? So we got to think about people, we got to think about planet, we got to think about society, and we got to think about technology that works, because there's nothing sustainable about technology that doesn't work. Right? So this is the triple bottom line, the sustainability triangle: economic prosperity, environmental stewardship, social responsibility. Okay. So this is a sustainability piece. Let's talk about life cycle assessment. And we can begin doing that by defining this idea of life cycle thinking. So I have a car, and maybe I'm thinking about not just driving it around and the emissions that go out the tailpipe, but I'm thinking about the aluminum and the steel and the glass, and where did all that come from? How was this car made? How did it make it to the showroom? How did it make it to my house? And what's going to happen to it when I'm done with it? All right, I can begin to think about all those life cycle stages. Maybe it's not ending up in a landfill. Maybe there's some reuse, remanufacture, recycle to try to close the loop on the materials so you don't have to keep extracting from Earth. But this idea of thinking about the life cycle is this idea of thinking about all the stages a product or a process might have. Not just the immediate, what's in front of your face environmental impact, but what happens upstream in production, what happens downstream in disposal. So as I'm thinking about that car, I'm thinking about the life cycle of it. If I happen to be maybe a manufacturing engineer, suddenly, like, boom, my head explodes into this. Right? And no way you're reading this, but what you're seeing over here is the raw materials that might go into a car. Coal, limestone becoming iron, iron becoming steel, bauxite becoming aluminum, copper ore becoming copper, lead, glass, plastics, pigments, into metal ingots, and plastic resins, and pellets that become fabricated auto parts that get assembled into the automobile and delivered to some dealer somewhere before it's actually sold. And then the car gets driven around. And it's not just the gasoline or the electricity the car might be using, or maybe even hydrogen, but it is the tires and the wiper fluid. Right? My folks got into a car accident the other night. It happened to be not insignificant, but they were fine. I learned about all these other things that go into having a car, right? A tow truck, hospital visits, overnight stay, etc. So that's part of the life cycle. Let's think about what happens to the car at the end of life. The big shredder that cuts up the car, and the magnets that pull out the steel, and the eddy current separators that take out the non-ferrous metals, and what happens, maybe the alternator gets reused or what have you, right? So this is massive. right? And I start thinking about it, my head just starts to hurt. And, for those of you who can actually read this, and of the things maybe I talked about, did I miss anything? Good.
Transportation, getting it from one country to another. You didn't talk about that.
Well, if it was, if it was made in Germany and brought to the U.S., that's part of the distribution system, right? Maybe that was on a boat for a while. Sure.
And then when we're done using it, then it gets shipped over to other countries, third world countries, because that's a big part of.
That doesn't actually happen that much. Western Europe, Eastern Europe, not so much in the U.S., but because of the expense involved and they have access.
There's a big business in Jacksonville. I just saw it this past summer.
Happens a lot more with cell phones. That in terms of our product ending up in, say, Africa or the Middle East. Yeah, sure, there are companies doing it, making money, but as a fraction of discarded vehicles, it's tiny in the U.S. But certainly things to think about. What else might be missing here? Roads, gas stations, bridges, signs, stoplights. Yeah, all that infrastructure, right? So now we could begin to think about that. All right? And, did I miss anything? We could keep going and going and going. Doesn't it take a car to make a car? Yeah, there you go, roadkill. You can bring that into the life cycle. But this is what life cycle thinking is, okay? It is unstructured, recursive, nonlinear, vast, complex. It would never be done the same way by two different people. It wouldn't even be done by the same person the same way twice. This is just thinking about what if, what could happen, what are the issues, right? That's what life cycle thinking is. And it is useless as an accounting instrument. If I want to answer the question, is that technology really sustainable? Isn't that accounting? Don't I have to add up what the emissions are, what the materials going into the system are? That's accounting, and it needs to be done. If two people do it, it has to be within error the same, right? So life cycle thinking won't do. Life cycle assessment will. And life cycle assessment is a standard. When you hear life cycle assessment, you should hear accounting. And it is just as boring as accounting. Nothing sexy about this, right? It is boring, tedious. It's worse than accounting. I took an accounting class way back when. This is more tedious, right? Because it's not just financial rules. There's interpretation about environmental issues that might range from future generations and climate to water quality and water access today. So the definition, as defined by ISO, the International Standards Organization, in the 14040 series, it's a standardized methodology to evaluate the environmental consequences of a product or activity holistically across its life. So yes, it does look at those life cycle stages, but there is a right way to do it and a wrong way to do it. The only way to learn how to do this is to work with somebody who's done it. And you're not really good at it until you've done several, because there's some art to it, just like accounting. So what happens is you have to first figure out what's inside your system and what's not inside the system. Right? If I need a truck to make a truck, but the truck I need to make the truck, I'm only using part of that truck, and it's really only a small part of its life cycle, maybe I can exclude that. Well, what are the rules of exclusion? Well, until I really know something about the truck that's needed to make the truck, I can't really make that judgment, right? I need some experience, right? And there's some tradition about what gets included and what doesn't get included, right? So the boundaries of exclusion are really critical and really nuanced. Right? Do I include the roads? If I'm comparing a Tesla and a Chevy Volt, do I include the roads or do I not include the roads? Right? Part of defining the system under which you're doing the analysis. Now, I just defined a comparative LCA where I'm comparing two different cars. Maybe they have the same tires. If they have the same tires, do I need to include them in the analysis or not? So this is what's called a relative life cycle assessment, like when you're comparing two things, a comparative LCA. An absolute LCA of a Tesla wouldn't exclude the tires. Right? And you're not always allowed to exclude the tires. If the tires are the most toxic and important part of the system, even though it's the same in both, you'd still bring it up. You'd still include it in the analysis. So there are all these rules in life cycle assessment. But once you understand the rules, what it's all about is accounting for first what's inside the system, what's outside, and then you have to include the whole life cycle, otherwise it wouldn't be life cycle assessment. And at each unit process, you're looking at the raw materials coming in, the energy coming in, maybe the water coming in. You're looking at the emissions going out and the product coming out. And whereas the life cycle thinking system was very nonlinear, LCAs are linear. Standard LCA is completely linear. It means that if I make 1 million cars or one car, 1 million cars have 1 million times the environmental impact of one car. Right? And we know that's not true, right? But the LCA protocol is a linear system. Okay? So, and maybe by virtue of the fact that I walked into the office yesterday, you were spared a lot of the boring details of LCA, because I was going to get into that. But let me just give you the quick and dirty here. 4 steps of an LCA. Defining what the goal is. Is it absolute? Is it relative? What's inside the scope? What's not in the scope? Where am I going to get the data? Once I do know where I'm getting the data, I go collect the data. The inventory stage is quantitative. It tells me how much water, how much energy, how much air emission, how much water emission, and each type of emission. So if it's a greenhouse gas category, it's the methane, the nitrous oxide, the CO2, the CFCs, etc. So the inventory just gives me all the emissions. It's a giant Excel spreadsheet, giant. Even for a simple product, it's giant. And then I take all that data about the emissions and resource consumption, and then I try to figure out what the impact are. And there are various impact analysis methods. And I don't just interpret at the end, because I have to start interpreting way at the beginning, because how I am planning to interpret the results and what I'm going to use it for influences how I set the boundary. Right? Part of the International Standards Organization process involves peer review. Right? Just like academics, many of you are researchers, right? So there's a peer review process that tries to make sure that the guidelines inherent to the 14040 series are held both in the letter of what's said as well as the spirit. So this is what, going from inventory now, here are the emissions, and this is just looking at the greenhouse gas emissions from some product. Again, the CO2, the methane, the nitrous oxide, the CFCs. Now I have to make a decision. Am I going to try to actually figure out, okay, I drove here today. It was a plug-in hybrid electric vehicle. I did burn some gas. I did use some electricity. So there was some CO2 released and some nitrous oxide released. So and maybe actually upstream some methane as well. So I have to decide, am I going to try to figure out how many disability-adjusted life years, this says daily, D-A-L-Y, how many people suffered because I drove here today? That's tough, right? Because I need to figure out, okay, which power plant supplied my vehicle, at what time, who breathed the emissions, how susceptible were they to asthma, particulate matter, cardiac arrest, because that's a big issue when it comes to power plants. Maybe mercury released. You think about eating fish that has mercury in it, some of the risks associated with that. That's nearly impossible. They call that an endpoint impact metric. And most practitioners of LCA don't even try to go here because the state of knowledge to do this is very, very poor. But what you can do instead is something in between to say, okay, well, I've got all these greenhouse gas emissions, and I'm going to try to just, instead of having like 5 different types of emissions, I'm going to talk about one equivalent emission of greenhouse gases. And I'm going to use what's called infrared radiative forcing, which has units of watts per meter square. It's basically how much warming these gases can cause. And there's a process through which you can take an emission of greenhouse gases and predict what the radiative forcing, how much warming might be caused. Now that warming might lead to drought, it might lead to different movements of different types of insects, and disease transmission might be affected, but we're not talking about that. We're just staying here in the middle. Right? It's called a midpoint impact assessment metric. Okay, it's not the actual impact, but it's something that we know has a relationship to the endpoint impact, and this is what LCA practitioners tend to use. So if I was doing an LCA of a refrigerator, and I did the inventory and a midpoint impact assessment, I might get this. So I've got global warming expressed here as grams of CO2 equivalent. And how did I create that equivalency? Through something called infrared radiative forcing. I have ozone depletion potential of a refrigerator because it has CFCs in the foam and the compressor. So I'm talking about how much potential ozone destruction is there. Well, in terms of grams of CFC11 equivalent, how many ozone molecules does a brominated molecule have the potential to destroy in the stratosphere relative to a chlorinated molecule? Right? So there's ways of creating this equivalency, and the technical uncertainty goes down tremendously. That's what people like about midpoint metrics. But they only loosely say something about what might happen. Right? But at least from an accounting point of view, it's hard to argue about the midpoint indicators because there's good science behind them. Right? And I won't go through all of these. If you're interested, I teach a couple of courses where we spend the whole semester understanding what these really are. Just plugging numbers in and trying to interpret this without knowing what photochemical ozone formation actually means, smog, and the fact that between 50 and 100,000 Americans die prematurely each year from breathing smoggy air. That's a pretty big deal that most people don't know about. From sustainability, that's a big deal because there are people who are not sustaining themselves. They die because they breathe bad air. Now, I don't want to claim that midpoint metrics are perfect because you remember this was the product of the whole life cycle. Right? Now, a refrigerator might last 15 years. Right? So this number of acidification potential or human toxicity, like when did that happen? Was it spread out over 15 years? Or did it all happen in an instant and affect one neighborhood somewhere? Right? This doesn't tell us. Right? And it's my view that engineers who create technology, who have the capability of producing these nutrition labels, also have the ability to understand what these metrics mean in a spatial sense and in a temporal sense, right? And can understand the basic toxicology that's involved with some of the water and air impacts. So that's what we do. I mentioned the program in sustainable engineering, the 9-credit program. That's what we do. We talk about impacts on the environment. We also talk about money. We also talk about social issues. And this is a very useful technique, life cycle assessment. Many of you, I'm sure, heard about the new aluminum F-150, Ford, going for fuel economy. Now, the deal with aluminum, I think most of you know, is that a kilogram of aluminum to produce it requires more greenhouse gas emission in production than a functionally equivalent amount of steel. So in other words, the production emissions go up in the aluminum F-150, but the in-use emissions go down. So what that means is if I have a lightweight, strong pickup truck that I never drive, right? It just sits in my driveway for 15 years, and then I destroy it, right? That was, actually the aluminum car was worse, right? Because it was all about production. You never used it. You never saved emissions relative to what the steel, let's say the regular conventional pickup truck was, right? And we actually did a study, I'll say for Ford, it was long enough ago, because they had a lot of questions about pushing into lightweight aluminum vehicles. What is the added production burden? And how long does it take to drive the car 12,000 miles a year before I actually get those emissions back before I'm on the right side of zero. So that's what this plot's showing us. Let's look at the black line. So what it says is I'm going to produce 1 car a year. It's an aluminum-intensive vehicle. The baseline here is 0. That's the conventional, let's call it a Ford Focus. Okay? So I've got the conventional Ford Focus, and I make 1 conventional Ford Focus a year. And now what I'm doing is I'm comparing that to a lightweight aluminum Ford Focus. And I'm making 1 of those a year. So in year 1, it took more production emissions, and there's only 1 of them on the road. So the emissions are higher. But over time, as I have 2 cars on the road, 3 cars on the road, 4 cars on the road, I'm only making 1 a year. The more I have on the road, the more savings I get. So after time, you're going to break even and do better than even. You're going to do better than you would have if you didn't lightweight the Ford Focus. Right? Now, what we discovered in this life cycle assessment work is that it really depends where you get the aluminum from. So if it comes from North America, your payback's going to be about 4 years. If your aluminum comes from China, you might be in upwards of 9 years, even longer, for payback. Okay? Now, this is just under one scenario. If I had a bigger car, it changes. And we did all that kind of sensitivity analysis work. But this is what life cycle assessment does. This is life cycle assessment's bread and butter.
Could you please elaborate what's the distinction between North America and China? Is it transportation? Is it?
It's the technology used to make the aluminum. So aluminum requires an electrolysis process. And that electrolysis process, if it's fed by coal, which in China it might be, versus hydropower or some mix of natural gas, coal, and hydropower in the US, then the emission factor in the US is going to be lower. It's more than that, but that's the basic issue. Now, if you go to Brazil, where all the aluminum is hydropower, it's almost carbon-free. And the payback time's almost right away if your aluminum comes from Brazil. Yeah, question?
Also include how much recycling of aluminum goes on?
Well, this is an interesting point because what all the studies before ours said is that, oh, aluminum's recycled. So this is recycled aluminum. No, it isn't. You cannot, it's not structural aluminum. And the only way you get to count recycled aluminum in the body and white of a vehicle is if you actually have recycled aluminum in the body and white. And that's not today, and that's not 10 years from now. That's not 20 years from now. Maybe it's 30 years from now. And the reason is you got to build all of them before you can recycle it. And you actually have to separate out the alloy. If you get cast aluminum mixed up with the body aluminum, you can't use it as structural anymore. So this is, for all intensive purposes, not recycled. And over the lifetime of a decision that we're talking about, it's not. That's a great question. And so the metals industry has been arguing, especially the aluminum industry, that it is, and they're wrong. So we wrote a nice article that made them all mad, but we got it published. It was a lot of fun. No. In fact, metals, I can get into this for forever. So there was another issue. They claim that all metals are recycled. Paper is recycled more than metals are. It's completely counterintuitive until you look at the data. So they say like, oh yeah, everybody recycles metals. No, that's not. When you actually look at a kilogram of aluminum and how long it stays in the economy, it's like twice, and then it's gone, right? So it's more like a half to a third, just disappears, right? So landfills, basically. So there's a lot that goes into this, right? But we got to get to the chase here. I won't even get to the example I brought. But we're having a good time, I hope. See, life cycle assessment fits here, right? There are sustainability questions about aluminum-intensive vehicles that this study didn't answer, right? Let's ask some important questions. Will people buy aluminum-intensive vehicles? LCA doesn't answer that. But if it's just a good idea and it sits on the shelf, it doesn't really contribute to anything sustainable. Right? It's just a good idea. Will producers make aluminum-intensive vehicles? In other words, can they make money? Because even if people want them, if producers aren't incentivized to build them, no, it's just a good idea. Where will the aluminum come from? That really matters. Brazil, North America, China? Life cycle assessment doesn't answer that question. That's economics. And imagine if Ford, GM, Chrysler, VW, everybody goes aluminum. We're going to need more aluminum. What's going to happen to the price of aluminum? It's going to go up. Price of aluminum goes up. Are people actually going to be incentivized to make the vehicles or buy them? Right, so there are all these effects in sustainability. And maybe people are afraid to buy the aluminum F-150. Right? Maybe, I'm somebody who thinks that this global warming thing is just a hoax, and by buying the aluminum one, yeah, I can save money on gas, but I'm going to make a statement that this global warming thing is just a bunch of BS, and I'm just buying the conventional one, right? Because that's how people are, right? I'm not saying that that's actually true in this case, but there are people issues as well. And by the way, what got that aluminum F-150 into play anyway? Increased corporate average of fuel economy standards, right? Policy, right? That was at the core of it. So if you want to actually begin to answer sustainability questions, you need a lot more than LCA. Let's talk about corporate average fuel economy standards. Because in the US, if you are GM and you make bigger cars, the target you have to hit's lower. That's how the corporate average fuel economy standards are written. The Environmental Protection Agency said cars won't get bigger. And here at the University of Michigan, we said, how do you know? They said, here, look at this graph. We looked at the graph, says, that doesn't say that. But we didn't have a methodology that would combine economic effects to say something about the environment, so we invented one. And this is work we did in my lab with support from the National Science Foundation. And the method we developed was called Consequential life cycle assessment with market-driven design. And what this is it's an acknowledgement that life cycle emissions are a product of the economy. And if we have different technologies available to us and different policies available to us, well, supply and demand might react differently. If I put a gas tax on, maybe people are going to buy cars that have higher fuel efficiency. And different technology will get sucked into the market, which will lead to different emissions. This method we have a lot of practice with, and I don't have time for the case study, but you have to begin to get into supply and demand and policy to understand what technology actually makes it into practice and what the real emissions are. So this method here at least gets two parts of the triangle, right? It gets the economic aspect, the environmental aspect. It gets a little bit of the social piece, but I won't say enough of it to circle this over here. All right? And actually, when you have an analysis that looks at the economic aspects and the environmental aspects together, that's called environmental sustainability. It's not sustainability, it's environmental sustainability. It's two of the three. Right? And you never want to ignore the social issues. But often from a quantitative point of view, these are hard, right? So you basically do your analysis here and then say, okay, well, if you're allowing cars to get bigger, are there going to be social impacts of that, right? People are going to be incentivized to buy bigger cars and things like that. So, at least with this methodology, we can get two of the three triangle points on the triangle. So let's spend a few minutes on this. So what's wrong with this picture now? Yeah, life cycle assessment cannot tell you. It gives you important information along the way, but it's a third of the story. Okay, and that's the key thing here. We got to bring it into economics and bring it into society if we want to actually talk about sustainability. Thank you. Go ahead.
Oh, gosh.
Yeah.
Wouldn't the social responsibility play a part as the policy from the government and things go into the different environmental and economic standards?
Yeah, it does, but it's not the whole story, right? Because certainly the people in Washington don't always represent our interests in the public good and the greater good. And even if they are doing that, there may still be individuals negatively affected, maybe just one or two, but we got to think about them too. So yes, and economics gets part of social issues as well. Right? Think about education, employment, things like that. Money is part of that as well. So that's what I said. It kind of bleeds into this, but it's certainly not the whole story, and that's why I didn't circle it. Okay, so that's the message here. So let's just take a few minutes and talk about how to approach sustainable design. Okay, so here's a definition, and if we're going to talk about a technology, now you're beginning to see, like, wait a minute, sustainability is about quality of life, largely of people who don't live as well as us and future generations. So when I talk about this iPhone, is it really like about sustainability? Well, yeah, it can be because of access to resources, both abroad and, or I mean, look, they're impoverished places here in the US as well, let's not kid ourselves. But also for future generations, right? But it's a much bigger thing than, is this phone a little bit more efficient? Or did we turn the lights off? Right? It's not efficiency. Efficiency doesn't get us sustainability. Efficiency is what we should be doing anyway. Sustainability is a bigger thing. And so if we're going after that, well, maybe a definition could be, you know, achieving sustainable design when you achieve economically viable designs that significantly reduce important environmental and societal concerns and do so much better than the other available options. Right? At least we can measure this, and we know we're moving in the right way, but it's transformative. They fundamentally alter our pattern of use. Right? So when you take, you may all remember answering machines, right? And you just have voicemail, like that's transformative, right? That's not efficiency. That's just a way better way of doing things, right? And so we call that transformative. Now, just doing answering machines, voicemail, it's not going to make the planet more sustainable, but at least you're going in that right direction. And where people might draw the line is certainly arguable. So there's something about magnitude of impact, and there's something about transformation, because we're not getting the sustainability on the path we are. And policy, it may be all about policy to create the level playing field for sustainable designs to actually make it in the market. So what's a model? And I teach a whole graduate class that's trying to give students practice to come up with sustainable designs. It's a very frustrating business. And if I had time for my example, I'd show you why it's so frustrating and so hard. This is a slog. It's you know, coming up with something 10% more efficient, that's easy. Pretty much any factory I go into, finding 10% energy efficiency, no problem, and it actually pays them back. But find 30%, 50%, starts to get hard. So let's just invert the sustainability triangle, and let's talk about prosperity up in this corner, and industry through creating jobs and creating products, you know, help to create that prosperity. Consumers pull product into use amongst a certain regulatory playing field, as we were just discussing. But as this happens, you know, there are these other issues, planetary issues, societal issues, that are not being addressed. These are called externalities by economists. Okay, so let's now say, okay, well, companies being able to provide products and services, that leads to prosperity. And people who are willing to pay for those products and services, or maybe don't have an alternative to buy a particular incandescent light bulb because it's banned by law, right, under a regulatory playing field, right, that influences the pull. Right? And when I look at the intersection of these two circles, right, that's today's market. And we know that there are issues way out here that are left out, right? Externalities, social and environmental needs. So if I'm trying to do something sustainable, I really need to be addressing these needs, but not in isolation, right? I need not just to have an idea for a more, a car that has lower emissions, but I need maybe a business model, or maybe I need technology to allow a company to provide that service. And of course, people need to be willing to buy it, or regulation needs to encourage it. And only under those cases will you have a sustainable design. Okay? So this is everything. Now, life cycle assessment tells me something about the environmental needs here, but it doesn't cover any of the rest of it. So engineers need to understand life cycle assessment. They need to understand how to interpret life cycle assessments and what the environmental impacts really are. They also need to know how to deliver solutions in a way not just they think people will buy them, but people actually buy them, or to get themselves engaged in policy to help actually make regulations that encourage sustainability. Right? So this is what I would call the relationship between life cycle assessment and sustainability. And I only left 4 minutes for questions, but if you have questions, we can take some in a few minutes we have left.
Coming over. The whole point of this project is to be able to see how a soldier can move through these obstacles, and then we're going to weigh them down with body armor.